Okay, so there's this thing called the Collatz conjecture. Pick any number you want. If it's odd, multiply it by 3 and add 1. If it's even, divide it by 2. Just keep repeating. And the conjecture was, hey, it seems that all of these numbers end up going to 1. Megomorph? Yeah. Pascal's pyramid. I mean, I think it should be Liu Hui's pyramid, but alright, cool. Right, so I try to give credit where credit is due. Liu Hui was the first one to build out that triangle as a number theoretic type problem, where it's just, let's see what happens when we do this. We'll follow rules and see where it goes. It has no real connection with anything. It just was, here's a set of rules, let's follow them. Al-Karaji realized the connection between the binomial distribution and polynomials. Like taking polynomials and saying, oh, well, if you multiply x plus 1 to the 4th power, then our coefficients are going to be 1, 4, 6, 4, 1. And then all of them are going to be broken out. Again, a to the 4th, b to the 0. A to the 3rd, b to the 1st, etc. And it was Pascal who realized that this could be used for binomial probability distribution. So his particular area was a very niche corner of mathematics. It was not, in fact, the discovery of all of this stuff. So the Collatz conjecture, yeah, we have not discovered any number anywhere so far that does not reach 1. All right, so somebody has set a computer on it and said, like, go find some number out there such that this does not work. Or it reaches a loop. If it ends up reaching a loop, then it's created a loop. That's really cool. And it didn't reach 1. So my favorite thing to do with this was, if you end up trying this out, create a map. So I'm going to pick 20. Right? 20 is even, so that's 10. 10's even, so that's 5. 5 is odd, so that's going to be 16. Triple plus 1. 16 is even, so divide by 2, that's 8. And then we're going to get, since this is a power of 2, it's just going to go straight down through here, right? 16, 8, 4, 2, 1. 1 is odd. Triple it and add 1. That gets us back to 4. This has created a loop. So 4, 2, 1, 4, 2, 1, 4, 2, 1, etc. Right? So now somebody else could pick a different number, 17, say. And then we say, okay, with 17, we're going to triple it. That's going to be 30, 51, plus 1 is 52. Divide by 2 is 26. Divide by 2 is 13. 13 tripled is 39, plus 1 is 40. Halved is 20. Hey, look at that. So our 40 goes over to the 20 like that. Yeah, so Caramel, I need to warn you, right? The Collatz conjecture is essentially... Hey, there's the question I wanted. Good job. Parfait. All right, and that's how I know you're going to do great. So yes, the question is, how do we build this backwards? And then from where do we build all of these things? Now, I actually do have somewhere a sheet of paper where I started writing down all of the connections that I had, which started from, again, 421, building all the way back out until I got to 1 million. on every single branch. This creates a giant tree. So I said, let's try to find every single number that we possibly can, just for fun. Now, other people have heard me say this before, but this is essentially my mandala. This is something that I just, color in for fun. You know what? I'm probably not going to find it in the next half hour or something like that. So we'll see if it's in either of these two notebooks, and if not, oh well. That's NCTM, so no. Right? No. And this one looks like scrap, so probably not. No. Yeah, it's in neither of these notebooks that are first things to hand. I could probably figure out where it went pretty soon, but... Yes, so if you can actually find a pattern on which you could find a number on this list that exists here and say, I know that if I wanted to work backwards, I could pick, let's say, 16. What would come to 16? Well, first of all, we've got the 5 there. But also, we could have had an even number, which then got divided by 2. So that would have been 32. Which would have come from, potentially, 64, which would have potentially come from 128, which would have potentially come from 256. So again, powers of 2 are super nice. Then, we could also say, well, what about these other numbers over here, right? We could have had 80 come to 40, and then 160, and then 320. Like, those are all even numbers, so if they just divided by 2 the whole time, they would have made it down there. So I think you're probably going to notice a question right here to say, like, okay, where are we going to come up with these branches? Where do they branch? So, Megamorph. It's all good. Ban. No. So if you understand modulus notation, modulus mathematics, you're good to go. You can use that as a hint. If you don't understand modulus mathematics, awesome. Just ignore that. Or put it in a notebook somewhere and you'll figure it out someday. But yeah, so I made a, like I said, I took a notebook paper, everything. I took a, standard 8.5 by 11 sheet of paper from the United States, because it's not A4. And then built out that tree in like every possible direction. And it got really big. Like I said, I worked out, okay, once I found a number, we're just going to keep doubling it until we go off to 1 million. And then it doesn't take that long, right? And then here we say, what does it branch? Does it branch? And then we find where those branches are. And we say, from those branches, those all multiply by 2 over and over and over again. And then where do those branch? Etc. You're just here for the quality company. So not quite. You're not going to ignore them. It's just that this... Right? And this is going to continue off to infinity. All those powers of 2, the direct powers of 2, are going to be kind of like your spine. It's the central piece that just keeps running up the center of the paper. And then we get these branches. Or trunk, I suppose. If we want to go with the tree metaphor, right? Right? And then here... going to be a branch. Right. So that's also an interesting problem, Megamorph, is some of them don't work. It's pretty obvious why they don't work. But you know, we can let that one sit for a minute. But yes, you're absolutely right. This is one of those problems that like everybody thinks they've got a solution to it somehow. And no. This is actually an exercise in patience, and like I said, for me it's a mandala. It's making something beautiful. I have no need to solve it. I don't care. I don't want to solve it. That's not the point. It's just pretty much exploring what kinds of patterns do I see here. Are there interesting things that happen? Are there a lot of runs where we get a lot of branching? Are there runs where we get no branching? You know, just looking at these things makes it interesting to me. What if you had a graph of the values? So it has also been done to look for a graph of number and number of steps to get back to 1. This has been done. It's really cool. If you figure it out just for yourself, again, know that this has already been done, but that is something that you can check and take a look at it and be like, oh, well, that's really interesting. Let me see if I have the same answer as this other person. Again, I would recommend you do it yourself and then maybe go and check it. See if you get the same picture. Yeah, so, you know, obviously 1 is going to be 0 steps because it is that, but 2 is going to be 1 step, and 3. We don't have 3 here, so it's up there somewhere. Don't worry about it. Oh, 3 goes to 10, right? So that would be 1, 2, 3, 4, 5, 6, 7. Right, and then 4 ends up being 2. And then 5 we've also got on here. That's 1, 2, 3, 4, 5. Oh, yeah, I mean, by all means, go for it. You could play around with it and do anything you want to try to find like some interesting thing. Anything that interests you with this, right? Just again, you can find an interesting pattern that no one else has found. I guarantee it. I don't know what it is. It's probably not going to be super easy, but you could go off and explore the wilderness out there and find something super interesting. Just again, think to yourself that, okay, probably somebody else has found this before me, and it's not going to be like a solution. It's just going to be something interesting and cool. But once you find that thing that's interesting and cool, like, you can talk about it. You can be like, hey, I found this thing. It's really cool. Slides from Terry Tout. Nice. Yeah, he's... I mean, in addition to being a good like, everything. He's also a really good teacher. I watched video of one of the classes he taught, and like the kids in his class, he says something. I don't even remember what it was now, but he says something, and it's like hinting at something that's just beyond their reach, and they're like, no, and all of them start scrambling for paper to try and like work at something. Recurrence reasoning. Okay, so I think maybe you're talking about implicitly defined sequences. So something like a sub n is equal to a sub n minus 1. I mean, even just the Fibonacci sequence, right? Add the two previous numbers to get the next number? Maybe? Recurrence relation, or implicitly defined. Not really. Okay. That's fine. Anyway, this is the Fibonacci sequence, and there is no explicit form. A sub n is a function of n alone. Alright, this is... What? That's false? What? Binet form... Oh, get out of here. Okay, yes, fine. You can use it doing phi divided by the square root of 5. It's a function of phi. All right. Fine. Gross. First C when n equals 0, then... Oh, yes, okay. Inductive reasoning. No. Nice combinatorial interpretation of it as the number of ways to write n as a sum of 1s and 2s. Yeah. The other one to do is recurring fractions. So phi which is equal to 1 plus the square root of 5 over 2 is, oops, right. That's not technically phi, that's going to be 2 phi. Almost got away with it, if it weren't for you damn kids. Yeah, so phi is equal to this whole thing here. Wait, hang on, did I? No, it is, okay. It does have a divide by 2. Okay, never mind. Next question, is that really just messed up? No, okay, it is all divided by 2. Okay, we're good. We're good. Never mind. Yep. Yep, if you take consecutive numbers in the Fibonacci sequence, it's about the right proportion. Which is like a really weird coincidence. Naturally, it's going to get further and further off the higher you go, but let's be honest. Nobody's going to care that much. By the time you get to the... Oops. By the time you get to that particular, like, order of magnitude, right, your error is also growing. Yeah. Oh, I guess your percent error stays the same, right? Oh, no, there are two moving parts. Okay, never mind. Just ignore me. It's all good. You do anyway, but... so anyway, recurring fractions here. Phi is 1 over 1 plus 1 over 1 plus 1 over, and continue that forever. It's just like one of those really wild things that works. And you can vary all of these numbers here to change what you get down the line for any irrational number to end up getting a recurring fraction that has a particular pattern. Now, it may not be a nice pattern. It may end up being, yeah, you could do it with any number you want. If it's of finite length, i.e. it is a, if it is of finite length or it repeats, so the number is rational, then you don't need this recurring fraction thing, or it'll end up being finite, so of finite length. But yeah, sure. So again, it may not have a nice pattern to it. Like, phi is all ones in those 1 plus terms underneath. So, like, any number you want, you can end up with... you can end up doing this, and your A, B, C, D, E, etc. will have some sort of pattern to it. Again, it may not be a findable pattern. It may be too hard, like, to actually figure out. So here's the thing, Mean Machine Rex, is that this is infinitely long for any irrational number. For rational numbers, it will terminate. And because it's going to terminate, then it ends up that you could just back it up, roll it back up all the way through, and end up making it a single fraction. Right? Because I can multiply both top and bottom of these things by a certain number, which would then collapse the that particular denominator. And then we could roll it back up term by term by term. So if I wanted to do some ridiculous, like, here, let's do
3.71417963014179.
So, what are we doing? 141799630. So if I wanted to do that, right, now I may have to go get my calculator because, just cause. And I may regret actually doing this, but it's fine. So one of the things you could do is just take off any of the stuff you don't like the 3, and just be like 3 plus, and then work on the rest of it as a recurring fraction. Yeah, so we could just make it 3 plus, and then here, instead of doing ... we say that this is going to be, right, 1 over, right, to get a 0.7. Oops. There is probably an efficient way to do this, and I don't know it. Okay, 3 plus 1 over 1 plus 1 over 2 plus 1 over Yep. All right. Caramel, have a good evening. We'll see you around, I'm sure. And again, if you have any other questions, there are many more math streamers. I suggest following all of us, because we can do all sorts of cool stuff. Answer any questions you've got, and yeah, have a good time. Hang out. I did not want that number to get bigger. Somebody wanted to learn category theory. Yeah, sure. I don't know if I have any prerequisite experience, but sure, I could be interested. Depends on what kind of. I mean, if it's like 3 a.m. here, probably not. But you know, hey. Holonomy, yep. Well, that's frustrating. I forget how to do this, quite frankly. How to make it nice. Nope. That number makes it smaller. Yeah. Okay, so if we bump that up to 9, what does that do to our number? 1.16. Alright. Not small enough, so back up 2 places and make that a bigger number. Too small. Cool. Rex, there's a real plane, a complex plane. Is there a pure imaginary plane? So, no, but there is a pure imaginary number line. Right, so the way that that really works is we've got our real numbers here, we've got our imaginary numbers here, and then all of this stuff together is makes up the complex. Right, when the real part of your complex number is 0. Yep. Don't know if you have a perspective that would be broadly appreciated. Okay. Proper plane? No. I mean, it's just a number line. You could, in theory, make a IR by IR plane. So, like, you could just make one. There's nothing stopping you. But I would argue that this simplifies to real by real. And if you wanted to, you could, like, you know, essentially factor out your I. It's not factoring, but like if you needed it for some reason, right? You could make one, but it's not going to be it's not going to be a true imaginary number plane in the same way that you don't have a true real plane. You have a real number line and an imaginary number line, which together can make a complex plane, or they could be paired with like kinds to make their own planes in R2. Something that I have been suggesting to my students for quite a long time is Welsh Labs came out with a series called Imaginary Numbers Are Real. And if you take a look at, like, this is a 10-part YouTube series. This is actually his personal website, but nonetheless, it's all linked. And he just came out with a book of this, so that's also linked somewhere on his website. Supposed to go through some complex stuff, differential equations and matrices. Yeah. So the differential equations and matrices part that involves complex numbers is stuff that we talked about toward the end of our differential equations class, which is really cool stuff, which for the most part we're talking like eigenvalues of plus or minus I, for example, are going to yield a solution of y equals c1. I know you're not going to understand this quite yet necessarily, but the it plus c2 e to the negative it, which then simplifies to y equals c1 star cosine of t plus c2 star sine of t. There's some just really cool stuff that goes into there. If you're a pure finitist, you can believe that real numbers are imaginary. Yeah. Yes, that is true. Of course, it was developed by René Descartes in order to discredit such imaginary numbers. It's just only that the name stuck, and much to his irritation. Yep. Okay, cool. So, the eigenvalues from differential equations end up and eigenvalues from linear algebra, right? They're all connected. They're the same thing, realistically. We ended up doing domain coloring. Yeah. If you end up doing stuff like, right, y1, y2 is equal to, and then have each of these be related to a x1 plus bx2 cx1 plus dx2, right? All of this stuff. Wait, hang on. There we go. Differential equations. Right, this ends up being that our y prime vector can be equal to ABCD times our x vector. Just x vector, right? Not prime. Yeah, just x vector. So if we want to solve the differential equation that involves this particular thing, then that's going to involve your eigenvalues, which find the steady state. Right, they find your steady state vectors, so along what particular direction are these going to point, and then the multiplier to tell you how big or how small that vector is, or if it's been flipped in the opposite direction. And syntax, if you check out my my series on differential equations that's in our channel here, then you can find like a bunch of this stuff that'll help explain it from a slightly different perspective. My point was that I went first with first order systems. And then I went with second order DEs. It's my channel. So if you just go into click my name down there somewhere, and it should list out a whole bunch of videos. If you click on like playlist or group or something like that, yeah, the VODs. If you click on the it's not playlist. What was it called? I don't remember what this platform calls it. Collections, thank you. Yeah, that's the one. So if you click on collections, you should see differential equations in there. I believe it's called class time differential equations. And it should be somewhere around, let's see, we got 20 videos. It should be around 8, give or take. So we only did partial differential equations for a couple of problems. We were looking particularly at exactness. And so we wanted to look at how a particular kind of differential equation ends up showing up in ordinary differential equations and can be, you know, we can leverage some of our Calc 3 type stuff, the vector calculus, in order to solve that. The way that I did it, I find probably pretty easy compared to, say, the way that the way that I was taught, which I did not teach. It's an option, but I don't like it. Before PDEs, yes. I think you have to. Partial differential equations is usually either a senior level math majors class or a math masters class. So you're not doing it before then. I think at my school it might have been only graduate level. I don't remember. It's been too long. I didn't care. I was math education. But yeah, I don't think it was on my list of possible electives. Pretty sure that I had 2 senior level math electives that I had to take or something like that. And I did linear algebra, senior level linear algebra. Yes, high school. No. Sorry, college. So bachelor's, senior level bachelor's in mathematics, in math. You're not going to be taking it if you're doing math education, typically, unless you're planning on going on to higher ed, which I was not at the time. I was thinking that I was going to be a high school math teacher for the next 40 years of my life. All right. Nice. That's pretty cool. Does the physics teacher also teach math classes? Or is he just like a supervisor for also the math department? Everything in a circled area just canceled out? Yeah. Alright. I will continue to answer any math questions you want, but we're going to hop over to Satisfactory, I think, which was the voted on item for tonight. So, let's see. We were doing... kill this music here. Let the game music come in. He's only taught you physics. Okay, gotcha. Which makes complete sense, yeah.